All right. Do we have all the speakers here? I see Shalmalee is definitely online. Hi there. Is Sara there? I at least haven't seen you in the list of participants. And also Mike Lau is still hopefully here. Anyway, Shalmalee, do you maybe want to go ahead and start sharing?
Yeah.
Oh, great. Thanks, Stephanie.
Can you see my screen?
Yes.
That's great. Oh, I have.
Great. Yeah. I guess we're all used to the format of 12 minutes talk plus 3 minutes questions. Shalmalee, would you like me to interrupt you visually or by voice?
By voice, please.
Voice, easy.
Yeah.
Okay, can do.
Thank you.
Is 2 minutes before the end okay, or do you want more?
Yeah, that's fine.
Easy.
Yep, thank you.
All right, great. I'm also monitoring the Slack, but I think we can just get started. So, Shalmalee, feel free to take it away.
Thank you. Hi, everyone. Thank you for giving me an opportunity to talk at this meeting. I'm seeing two different screens, so let me make sure that you're actually viewing my slide screen.
We at least see the slides, but we also see your doc.
Both of them?
No, we only see.
Wait. So can you see my screen now?
We at least see the slides and the movie. Yeah.
Yeah.
So I think you can just get started.
Okay.
Easy.
Okay. Yeah. So hi everyone. Thank you so much for giving me an opportunity to talk at this meeting. Today, I'm going to talk about multiple stellar populations and the techniques to find these multiple stellar populations in the Magellanic Cloud star clusters. I work with Richard de Kreis and Dan Zucker at Macquarie University. So let's get started. So why do we actually study the star clusters? Star clusters are basically very useful to determine the distance scale of the universe. We can also, by studying the chemical evolution in these clusters, we can connect these evolutionary stages with its host galaxies. These are excellent examples to test the stellar evolutionary models. So these are some of the basic reasons that we need to study the star clusters for. So why do we then study the clusters which are residing in our nearest galaxies? Why not just study the clusters which are present in our own Milky Way galaxy? The main reason for that is Milky Way galaxy doesn't have a lot of young or intermediate age star clusters. When I say young or intermediate age clusters, I consider these clusters in the range of 1 to 3 giga-year-old, and the old clusters in the range of more than 7 giga-years old. So our own Milky Way galaxy doesn't have that many young intermediate age clusters. So we have to rely on other young clusters which are residing in our nearest galaxies. The other reason is Milky Way galaxy is very old with low level of star formation rate. And even if we have certain amount of a certain number of young clusters in our own galaxy, these are very hard to observe as they are hidden behind many magnitudes of extinction. On the other hand, Magellanic Clouds, which is our nearest galaxy, has a lot of young and intermediate age clusters. So they offer easy access to study these clusters and the ongoing star formation in these clusters. to understand to understand the chemical abundances in these clusters, to connect these abundances with our Milky Way galaxy, so that we can understand and explore more about our own galaxy. So enough about the introduction. So one of the two of the main assumptions which are now wrong were that I think Maddie mentioned this yesterday. One of the ways that the globular clusters can now be defined is that nearly all of these globular clusters, with certain some exceptions, they have multiple stellar populations in them. And another assumption which is now wrong is that clusters younger than 1 giga-year-old or 3 giga-year-old, they don't have any evidence for multiple populations. So we categorize the stellar populations into two types, which is, one is simple stellar population, which can be defined as with the parameters such as same age, same chemical composition, with only difference in mass. And the multiple stellar population is it can be defined as with multiple isochrones, that is variety in age range, different rotational rates, and combination of chemical compositions. So in this slide, I'm showing two clusters, one with very young age, around 1.9 giga-year-old, NGC 1978, which shows multiple evidence for multiple populations. And the second picture in this slide is the one which is very old cluster, which also shows the evidence for multiple populations in it. So you can see that these two clusters with that huge age difference, both of these have presence of multiple populations. Now I'm actually more interested in studying the clusters which are young in age, and I largely focus on the RGB stars and the detection techniques for finding the presence of multiple populations in RGB stars only. So that's why I in my last paper, I considered 3 clusters which are around the same age as NGC 1978 and relatively massive, but we still didn't find any presence of multiple populations in it. So the question now arises as to which factors then affect these multiple populations. Is it just the mass? If that is the case, then all these clusters that I have considered, NGC 411, 1718, 2213, they should have actually shown presence of multiple populations, but that is not the case. So then we went ahead and we started to study another cluster which is relatively the same age. In NGC 2173, we found presence of multiple populations, which can be seen as one of the techniques to find multiple populations is to draw the fiducial line and distribute the distance distributions in it, and then you can see the bimodality in this cluster in this sample of RGB stars. Another supportive argument to give for this test was to study the distribution of RGB stars with another statistical analysis, which is the Gaussian mixture model, and it also detects the bimodality of the cluster. So that was one of the questions that seems very disturbing to me, that which parameter then affects this kind of presence of multiple populations in young or intermediate age clusters. So as I described, there are various methods to detect the multiple populations. One is just seeing the multiple stellar streams in our CMD, which in this case, my first paper about NGC 411 and other clusters, which clearly does not show any presence of multiple populations in it. Second one, as you can see in this figure, the bifurcation of RGB stars at the tip of the RGB, that can be one of the detections of multiple stellar populations. Another example, Maddie also mentioned this yesterday about the UV photometry by using the C index, the color index of HST filters. So the reason why this works is because UV filters are very sensitive to certain chemical molecular bands, and as a result of this, second generation, as you can see, second generation of stars which are enhanced in N, but they display the Fenter magnitudes, but they are bluer in color, and the first generation are redder in color. And this, as an example of NGC 1978, shows bimodality in its RGB stars. We also studied this in case of NGC 411. We unfortunately didn't have extreme U band filter, but we managed it with F336 U filters and other B and I filter. But we couldn't find any presence of multiple populations in NGC 411. One more technique that is very prominent in and very much important to study this multiple stellar population is the magic trio, as Maddie yesterday mentioned in her talk. The same is the same reason. This is also one of the famous examples of 47 Tuc, and you can easily see in its color index with the extreme U filters, you can see multiple stellar streams in every evolutionary stage. And the last technique that I also use in my research is the chromosome map, which is just the plot of two pseudo colors. One difference between the previous magic trio filter combinations and this chromosome map is that these chromosome maps include the white baseline color. So from U to extreme I range in wavelength, you can plot these pseudo color diagram in terms of using three filter combination and the two normal color combination, and you can see in 47 Tuc old globular cluster that the 1 and 2G generations of stars are clearly visible. And so thank you. So the reason why we include these techniques in our research is that to understand the chemical evolution of these clusters. Oh, 2 minutes. Okay. One of the major reason is to understand the helium content in our clusters, in our nearby galaxy clusters. Helium is very difficult to measure by spectral lines, and that's why we mostly depend on photometric inference of these helium content. Another property that we can understand by studying these kinds of stellar populations in young and intermediate clusters is understanding the two distinct properties, two distinct generation of stars, as I have shown in the previous slides. One more assumption in earlier ages was that these multiple stellar populations depend on individual stellar mass, which now is not the case. The general understanding now is that the multiple stellar populations occur in clusters which are around or more than 1.5 into 10 to the power 5 solar masses. So that is now very clear. And another reason, another property that we can understand by studying the multiple stellar populations in young clusters is that we can then understand more about the types of two classes of globular clusters, which is type 1 globular cluster and type 2 globular cluster. So my understanding, and I really want to understand which kind of parameters are trying to determine these kinds of presence of multiple populations in young and intermediate age star clusters. So mass is definitely the factor, but I want to understand, is it the age or is it the combination of these clusters that can determine the presence of multiple populations in young and intermediate age clusters? So yes, thank you.
Awesome. Thank you so much.
Thank you.
Yeah, we can actually clap here. I hope you can hear that.
Thank you.
At least some of us can clap with audio. Do we have questions? We have one from Thomas Nolander in the chat, who's asking, well, first of all, thanks for the great talk. Could you gain anything by also analyzing spectra from MAVIS?
I think so. I'm not sure about it. I haven't read much information about the data which we can get from MAVIS, but I think I'm hoping to. Yes.
Easy. Okay. I'm pretty sure that Steph Monti, who is one of the MAVIS experts, can join the conversation later. We have another question from Gary da Costa. Any idea why NGC 2173 has multiple populations while 411, 17, 18, and 2213 don't? Masses and ages seem to be very similar.
Yeah, that's the reason why what I want to understand and explore that cluster more. I don't have the answer for that. It's a really good question. I'm trying to understand that, but I don't have an answer. Sorry.
Okay, then no worries. Good idea for follow-up research.
Yes,
and then
definitely.
I would say second to last question from Sara Martel. Do you think there might be different important factors in whether there are multiple populations in dwarf galaxies versus more massive galaxies?
I think so, yes, I think, but I wouldn't point on one particular parameter, but I think yes, there will be. I'm not sure how to answer that question right now. I'll need to think about it. Maybe I'll chat with her on Slack.
Don't worry.
Yeah.
Yes, that's the great thing about Slack. We can still think about questions and answer in more detail. And then last but not least, we have a comment rather than a question, but that's a really good one. Miguel says, "Happy birthday." Did you
Thank you.
All right.
Thank you. Thank you so much.
Thank you again for the talk. And I would say we go over to the next speaker. Thank you so much again, Shalmalee.
Thank you. Thank you.
All right, Sara, do you want to go ahead and start sharing?
Yes. Can you guys hear me okay?
Yes, we can.
Great.
Awesome. And we can see your screen. All right, good. Then take it away.
Great, thank you. So first of all, thank you so much to the organisers for letting me talk about fast flares. I love them and I'm excited to share them all with you now. And it's a really nice transition from the last talk, because if you want to study stellar flares, you should look at globular clusters, because you can gather a lot from their age. Okay. So I'm Sara, I'm finishing my PhD at Swinburne University of Technology, and my PhD was all about big data and looking at how to manage it and then what we can find out from it. And so I'll be talking a little bit about not only the fastest flares that we found in our galaxy, but some of the machine learning used to discover them. When you've got a lot of data, you don't want to do a lot of work. So I'll take you through that. But first of all, why do we care about stellar flares? And so there's a couple of reasons. One could be to better understand our own home in the universe, so to understand, is our star likely to flare? You know, in our human lifetime, we don't have any records of it, but what are the chances that a G-type star could have a massive flare event? Luckily, with research, we should be okay. But another, probably more important question is to better understand how life might form in other parts of the universe. So we know that about 50% of our galaxy is made up of M dwarfs, and they happen to be fantastic homes for rocky-bodied planets. And this is the type of place we're looking for life to begin. However, M dwarfs also happen to be the most flary stars that we have out there, and they flare for a very large fraction of their lifetime. So it's kind of this little bit of a paradox where you might have a perfect place for life to exist. However, does the flare stop the life? Or conversely, there's some arguments that you might need stellar flares to actually get life going when we're talking about being able to create different types of amino acids and then simple organisms. So there's a little bit of a trade-off there. So we need to understand where we flare in the universe and what that might mean. But most importantly for this talk anyway, we need to understand their rates and how it impacts the transient universe on a whole, especially when we're looking for really fast transients. So here are some anonymous quotes from my colleagues about how flare stars affect us, and they've been described as the cancer of the sky, the bane of someone's existence, and the foreground fog in almost every paper referring to very fast transients. So these transients might be kilonovae, they could be hunting for prompt gamma ray afterglows, they could be hunting for shock breakouts from supernovae. All of these incredible things that happen on very short timescales tend to be clouded by flare stars. And what is so difficult about flare stars is that they are coming from M dwarfs most of the time. M dwarfs are incredibly faint, not very blue, so often they're not picked up in whatever imaging you're doing until they flare and release very blue energy. So just a quick little overview to describe how pesky they can be. This is a luminosity phase space diagram, and all you really need to look at is that where we have the shortest events that we're trying to chase up in the transient universe, again, GRB afterglows, kilonova, core collapse, breakout, our flare stars exist within that time frame of being able to be a transient in this space. And although the magnitudes are very different, when you might only have 1 or 2 data points, it is very hard to distinguish whether something is a true extragalactic transient event, or is it a flare star from an M dwarf on the edge of our galaxy that no matter how deep our pre-imaging goes, we will never be able to see because the counterpart, the actual quiescent host of that flare is so faint that it is not observable with some deep imaging. So this is a really tricky question, and if you're going to trigger the biggest telescopes in the world, 8 and 10 meter class telescopes, to follow up some transient events, you really want to know what is the likelihood that it's going to be a pesky flare. So just a really quick overview of what causes a flare star. It's a magnetic reconnection, and so M dwarfs, like I said, they are the most predominant stars in our galaxy, and they happen to be also the most magnetically active. And this is because the majority of them, when we get to late type M dwarfs, are almost fully convective, if not already fully convective. So they are very different structure to stars like our own and to some of the hotter, bluer stars. And this makes for a great opportunity for magnetic field lines to run wild, bump into each other, and release very high amounts of energy. So a little bit for how we found them in the work that I did. So there's a program called the Deeper, Wider, Faster program, led by Jeff Cookie at Swinburne. I'm sure you might have heard a little bit about it in Jilai Zhang's talk earlier in the week. Great program, and if you have any questions, please pop them in the Slack. But basically the program takes very fast cadence imaging with our workhorse optical imager, which is the dark energy camera. So 20-second cadence imaging, which means we're on the sky for 20 seconds, we read out for 20 seconds, and it just goes again and again for hours, which means that we have a cadence of about 1 minute between data points. So this is a phenomenal cadence and very different to what traditional surveys actually do. And even with only 20 seconds, you're still able to probe quite deep within the sky. So about 23rd magnitude when we're looking in a G-band. And just quickly, the reason we look in G-band is because the most energetic explosions, such as a kilonova, different types of supernova, and unfortunately flare stars, all are very, very blue in their colours. So far to date, DWF has had multiple both commissioning and operational runs, and all of my data that I used in my PhD was about 15,000 to now 20,000 images, and we have about 17 different field pointings. And as you saw on the previous slide, these fields are massive. They can fit several full moons in them, and each field of view image has many hundreds of thousands of sources. So in total, we have many millions of sources. And again, we have that beautiful cadence of about a minute in between. So how do we figure out how to look through all of that data for these millions and millions of sources to actually discover what we're looking for? And now this is another question, what are we looking for? So as transient astronomers, depending on what type of transients you might be studying, you don't want to bias yourself or put yourself into a box of what you're looking for. So for an example, if you use like a boxcar search over a light curve, you're looking for a very, very specific change in that light curve, and you could be biasing yourself to an incredible Nature paper-worthy discovery just because of your accidental close-mindedness when it comes to algorithmically searching. So we don't want to do that. We want to have a very open mind. We want to look for anything that is anomalous in the light curves. So to do that, again, we don't want to look at millions and millions of light curves, not only for our time, but for our sanity. We want the computer to do all the hard work for us. And thankfully, we live in the day and age of machine learning, and especially unsupervised machine learning, where we don't need to understand all of the priors that might exist for any type of transient that we're looking for. We can get the machine to just show us which ones are the most anomalous to the complete sample, and we can go from there. So that's exactly what I did. So one approach that we took was doing a density-based clustering algorithm. And so we used HDB scan, which puts them in different hierarchies. So traditionally, when you use a density-based algorithm, it's able to group like data. However, it will only look for a group of a certain size, which is not great when we know that transients come in all shapes and forms, and in a data set of 1,000 light curves, you might have 5 of one type, 100 of another, 2 of another, very different numbers, and they are not comparable when we're looking at the same density. So HDB scan with the hierarchies is able to filter them out and still contain them in their clusters. And to do this, we break down the light curves into features. So we, in the paper, my paper from last year, we broke down all of these light curves into about 25 different features. So we took that 2-dimensional light curve, broke it down into this 1D feature space, and was able to describe them via a variety of features. So there's just a few on the screen there. By doing this, we can then compare all of those features in higher level dimensional space. So all 25 features, we can compare all 25 for each light curve to one another. And this is where we start to see similarities forming in that higher dimensional feature space, because light curves that are very similar to each other are going to have very similar features once they are normalized. And this is how we start to find our groupings and our clusters. So this is just an example of one field, and you can see that when we use a TSNE to visualize the feature space in 2 dimensions, we see very clear groupings with different colors there. Now, this work was really, really interesting, and it produced a lot of really useful things. We were able to find steady light curves, variable sources, all sorts of things caused by misalignments and CCD issues. But the most important thing were these unclusterable light curves. So what this meant is these light curves were so anomalous, they didn't fit into any of those larger density clusters. And this is what we're looking for. We want the things that are rare in comparative to the sample. So from there, we can actually visualize them. This is now our time to look at the light curves. And to do this, we used Astronomical, which is a great package from Lochner and Bassett. And I highly recommend anyone with imaging or time series data, check it out, because you can run an isolation or a random forest with no experience. You just chuck your data in, you tell it to do it, and it will find you the most anomalous things. So that's what we did with our unclustered light curves. We ranked them based on how far from the sample were they, and then we discovered various things. One of those things that we discovered was that this algorithm was really, really good at finding flare stars because they were so different to the overall sample of steady stars. So our next work was using this DWF sample to do a distance limited study of flare stars throughout our galaxy. So we took 12 DWF
You have 2 minutes?
Thank you. 75 hours, thousands of light curves, and fed it through the same system. And what we found was not only beautiful flares like this massive one here, but we found these very, very quick flares like this one here. Very quickly, over within 3 minutes. These are the contamination that happens in all sorts of transient data sets. When you have something that goes from very faint, can blip up past detection threshold and fall back down very quickly. So with these studies, we were able to find just shy of 100 of them, confirm that they were mainly coming from these M-dwarf type stars, as shown in this modified HR diagram here. But most importantly, what we found is that there was a variety of different timescales for these flare events. So this plot here, although it looks very complicated, we're just comparing our sample of flare stars to other samples. And only DWF and the Galaxy team have so far published work on these very fast flare stars, so flares occurring under 5 minutes. And it is quite a unique region of this space if we look down here. Another interesting finding very quickly was that as you move out of the galactic plane, you get less and less flares, which is what we expect because of the evolution of the M-dwarfs. So this was a good confirmation from such a large sample. And then we finally also confirmed that those stars that are fully convective, like I said, more aggressive magnetic fields with more reconnection are the ones that flare most of the time. So thank you for coming on that flare adventure with me. I'll leave you with some papers that you might be interested in, and I welcome any questions.
Awesome. Thank you so much, Sara.
Thank you. Sorry, I'll leave that up for everyone.
Okay, that sounds great. Yeah, it's really awesome to see more of the data points in the flare duration versus energy diagram. I'm going to start with a question from Jake, actually, who starts by saying, first of all, brilliant talk, great science communication skill. skills, but he's asking about the light curves. Did you use the light curves for your TSNE, and could you use the likes of tests to grab more light curves?
Great question. So for the TSNE, we used the features that were derived from the light curves. So in essence, they were the light curves, but they were the features describing them. And as for TESS, absolutely. So as of this year, TESS is actually starting to take 10 and 20-second cadence, so very similar to DWF, but for their selective stars. Going to be a phenomenal data set, and I really hope I can get my hands on it one day.
Awesome. Ella Wong is asking, did you notice any obvious correlations between the feature space or maybe basis transforms if you looked at that and the clusters?
Right, yeah, another great question. So when we were deciding on what features to do, at first we had almost 100 different features, and we really honed in on the ones that focused on more the shape of the light curve rather than the actual differential change in the magnitude, because that can be so arbitrary depending on what you're looking at. So we really focused on features that really described the different shapes of the light curve, so things like kurtosis, and we even did some fast Fourier transforms on them as well. And yeah, haven't dived too much into that, but definitely something worth exploring.
Awesome. All right, Lachlan has a question. He said, it looked like you might have had a flaring white dwarf there in your HR diagram. Perhaps not your field of expertise, but any idea what that, why that might happen?
Yes, I know exactly what that is. Unfortunately, that doesn't have a confirmed color from Grail, so it most likely is an M dwarf, and the color puts it as looking like a white dwarf. However, we're fairly certain just from the shape of the flare that it's most likely an M dwarf. If it was a white dwarf, that would have been incredible, so sorry.
Yeah, exactly. Well, too many M dwarfs out there.
Yeah.
All right. Good, then we have... Do we have any other questions? In the meantime, I can just say that Sara loved that you're using this segment of the DWF data set. Super interesting. All right. If we have no other questions so far, then I would say we thank Sara again. Thank you so much. And we can move on to the next talk. Right, and if I'm correct, the next talk will be by Michael Hayden. I see you, awesome.
Yes, all right, let's see.
And I can hear you, great.
Can you see my slides?
Yes, we can.
Excellent.
Great. All right, then take it away, Michael.
All right, thanks for having me. I'm Michael Hayden from the University of Sydney, and I'm going to talk to you about chemical clocks and chemical tagging with Galah. And I want to highlight this work was done in close collaboration with Sanjeev Sharma, Jocelyn Hawthorne, and the rest of the Galah team. So why do we want to do chemical clocks? Well, ages are kind of the holy grail for galactic archaeology, but it's really, really hard to measure ages for most stars. And in fact, you can only get accurate ages really for stars you have astroseismology for. So stars like in the Kepler field on the giant branch, or for certain regions of the HR diagram where you can do isochrone matching. So I'm highlighting here why it's so hard to get ages using isochrone matching. So each track here is an isochrone of constant age, and the youngest age is 1 gigayear on the top left, the oldest age is 13 gigayears on the bottom right, and each different track is spaced by 1 gigayear. So that's 1 gigayear, 2 gigayears, 3 gigayears, and so on. And so you can see that on the main sequence in the HR diagram down here, all of the isochrones are stacked right on top of each other, okay? So that means if the star that you observe is on the main sequence, you can't use isochrone matching to get an age. Similarly, on the giant branch here, you can see again, the isochrones are very close to each other, so you can't do isochrone matching here either, except for maybe on the very youngest stellar population. So you can see there's a bit of separation there. So there's only really this special region right here on the main sequence turnoff area in the HR diagram where you can get accurate ages using isochrone matching. Now, the downside here is when you're doing a stellar survey, most of the stars you observe are going to be on the main sequence or on the giant branch. So most of the stars you get a spectra for, you won't have an age for. And so that's where chemical tagging or chemical clocks might come to our rescue for getting ages for these stars. So what is chemical tagging? So this idea kind of underpins all of galactic archaeology. So the idea is that stars contain the chemical imprint of the gas from which they formed, and stars born together share the same abundances. Modulo stars that are born in globular clusters that might have multiple populations from all the wonderful talks we've seen throughout this conference. But generally, stars born in open clusters anyways should share the same abundance patterns. So if you can measure enough abundances, you can actually tag stars to their birthplace based on the chemical patterns you observe. And you can use galactic chemical evolution to trace those abundance patterns and act as age tracers or chemical clocks for the stars you look at. And so this is kind of that idea in visual format. So this is a wonderful astronomer's periodic table from Chiaki Kobayashi in 2020. And so the x-axis on each of these elements on the periodic table is actually time. And so the key takeaway from this plot is each element you observe covers different nucleosynthetic production sites, and those production sites both produce different elements and on different timescales. So your type 2 supernova, stuff in blue, those go off instantly and produce a lot of alpha peak elements, so your magnesium, your silicon, things like that, whereas your AGB or type 1a supernova produce different elements and they have a delay time, so they don't ramp up their metal production right away. So if you can measure all these different elements together, they might tell you something about both where the star was born and when it was born in the galaxy. So what does that look like in practice? So I'm showing you now an alpha abundance, so magnesium to iron on the y-axis here, and x-axis is time, with present day being right at 0, and then age of the universe at 14 there. And so you can see there's a very nice trend of alpha abundance with age, particularly for old stars. So if your star is alpha enhanced, you can almost just directly estimate the age based on that abundance. And then as alpha lowers, the age gets younger and younger, and somewhere around 8 gigayears, alpha kind of ceases to be a good age indicator. You can see stars between plus 0.5 and minus 0.5 in alpha span a very, very large range in age. And so alpha is not a great proxy for age for these young stars, but for old stars, it's very useful. But that's only one element, right? So what happens when we take a different one? So this is now yttrium. Yttrium to magnesium. Yttrium is an S process element, so slow neutron capture, and primarily comes from these AGB stars that take a long time to ramp up. And so this is a beautiful plot from Neeson in 2015, using solar twins, and the stars can be very local to the sun just spatially in the galaxy. And you can see that yttrium to magnesium has a very, very nice trend with age. And so just based on this plot alone, you might say, oh, we're done. You measure yttrium and you get the age of a star, that's all you need. But the problem with this analysis from Neeson is that the stars are very, very local. And the stars that he looked at don't necessarily span a very large range in parameter space. So when you take a larger sample and do the same analysis, oh, disaster, right? We see kind of a scatter plot. We don't see that wonderful linear trend we saw before. And we see a bunch of scatter points. And actually, if you dissect it a little bit more, you might see some trends as a function of metallicity rather than just one global linear trend. And so this was a paper by Casali in 2020. And what they found is that the trends are separated by metallicity. And why might that be? Well, if we stop and think about it for a minute, take a star that's, say, 6 gigayears old. If it's very, very metal rich, so something following the red line, it was born in a very different environment than a star that's 6 gigayears old that's very, very metal poor, like following the blue line here, right? So in essence, these are tracking different birth radii or different locations in the galaxy, which have very different star formation histories. And so those different star formation histories mean you have different chemical abundance age relations. So it might seem like all is lost, but that actually might be helpful for us if each track is unique. And so that's one of the things that we have to look into. But the take home here is that you can't just fit a straight line to things and hope it'll be, everything will work out. It's a little bit more complicated than that. But we do need to test something that I just said, and that is, if you can measure the age and metallicity of a star or estimate its birth radius, how unique are the age abundance relations for that birth radius to that position? So this is what Melissa Ness did in 2019 using apogee data. And she took ages from astroseismology, so stars in the Kepler field. And then she knows the metallicity because they have apogee spectra. And she took the other elements from apogee and said, okay, I know the birth radius of the star because I know its age and metallicity. Can I estimate the abundances just from that, knowing that alone? So basically, is the age abundance relation unique to that particular position in the galaxy, or is it going to be a scatter plot? And she split the sample into metal-rich stars, metal-poor stars, and found that there are very strong trends for both subsamples, and that yes, in fact, when she does say, all right, I know the birth radius, I know the age and metallicity, I'm going to predict the abundance and then compare that to what apogee measured, and she found that she could recover the abundances to 0.02 dex, which is the measurement errors for apogee. So actually, all of these relations that she was finding do say that age and abundance, age and metallicity do uniquely define your abundance patterns, and those patterns are unique to your position in the galaxy. And she's recovering the accuracy to 0.02 dex. So that's really, really helpful for chemical tagging. Now, the downside of this paper by Melissa is that the apogee data really only has alpha and iron peak elements. So you can see magnesium and titanium and nickel, calcium, but there's no S process, no slow neutron capture, or no rapid neutron capture elements in the apogee data. And so this is where GALA comes in real handy. And so this is a plot showing GALA data now, and it might look terrifying, but this is just highlighting how useful GALA is, because we have abundances for 30 elements on the periodic table. And now we can take turn-off stars that we know the age for and do the same exercise that Melissa did. And I'll just highlight a couple here. So this is yttrium. So that's one of our S process elements. You can see there's a very nice trend of yttrium with age. Same thing with our barium. And then now we have europium here, which is an R process, which has an opposite trend, right? So it's europium, low europium is young, high europium is old. And so GALA is able to provide other nucleosynthetic sites and shows the same idea, same result that Melissa did. And so we do the same exercise, say we know the age and metallicity, how well can we predict the abundance, and what's the scatter around that relation? And the measurement uncertainties for GALA are a little bit worse. So 0.03 to 0.05x, which is highlighted by the dashed line here. And you can see the green triangles are how well we are able to predict the abundance just based on its position in the galaxy, its age and metallicity, its birth radius. So you can see for most elements, indeed, the scatter is quite small. So this means that chemical tagging actually should work. The age abundance relations are unique to a particular location in the galaxy or a particular age or birth radius. So as long as you can measure enough abundances, you should be able to then use the abundances to measure age. Just one more highlight from this paper that Sanjeev and I worked on. One of the nice things that came out of this is that elements that come from the same production site, so alpha elements or rapid neutron capture elements that come from type 2 supernova, all have very similar age abundance trends. So the age abundance trend is on the x-axis here, and you can see the alpha elements, your magnesium, your titanium, and your R process, your europium, they all have very positive age abundance slopes. Now, if you go to the S process elements, that's shown here in purple, you can see that they have negative slopes. So all the elements, depending on the production site, group together in their slope and the age abundance relations. And the other take home here is that each element does provide age information. And so you should use all of the elements that you think you are well measured in the spectrum. You shouldn't just use one like yttrium or magnesium. You should use as many as you can that you think are well measured. So that's what we're doing. So GALA offers us a way forward by providing all these abundances. And so we're going to use a subset of turn-off stars that we know the age for. And we're going to take stars with very good abundances to calibrate our age abundance relations. And these stars, we have enough of them in GALA that they span the whole parameter space. So stars from the inner galaxy, stars from the outer galaxy, stars near the sun. So we can actually learn all of these relations and do better than a scatter plot. Now, we're going to also be able to extend this to the whole HR diagram. So what we're going to do is we're going to use these age abundance relations from these elements that I'm highlighting here to do that. And we're going to use a machine learning algorithm. So rather than just fitting a simple straight line, we're going to use XGBoost, which is kind of a gradient decision tree algorithm, and these 13 abundances to try and estimate ages for stars. And so that's what the results of that are shown here on the bottom panels. The left one is the training set and the right one is the test set. So the test set is stars that we know the age for from, because they're main sequence turn-off stars, but weren't included in the training data. And so you can see that we are actually able to estimate the age just based on abundances to the accuracy of about 1 to 1.5 gigayears. So the isochrone age that we derived is on the x-axis, and that's accurate to also about a gigayear. So in essence, we're recovering the errors in our isochrone age measurements just with chemistry alone. So this means that we're now able to take chemical abundances and get you an age for a star accurate to 1 to 1.5 gigayears, and we can extend this to the whole the whole HR diagram, because GALA spans not just the turn-off region, but dwarfs, main sequence stars, and giants as well. And so you can use that, for example, to study the kinematic relations in the solar neighborhood, or extend them beyond the solar neighborhood now with not just turn-off stars, but the entire GALA sample. And I'll skip that in the interest of time. And so now I'm going to focus on what elements matter for these chemical clocks. So if you want to use chemical clocks to determine an age for a star, what elements do you have to measure if you're doing a spectroscopic survey? So this is what XGBoost determined was most important for a reliable age. And so I'm going to focus on the left panel here. And so you can see the top two were magnesium and silicon. So these are alpha elements. And I already showed you how useful alpha is in determining age. Basically, if you know a star is alpha enhanced, it's got to be old. And if it's alpha poor, it's got to be young. So just based on the alpha alone, you can split a star between young and old immediately. So alpha was a very good, important age indicator. The next one on the list is yttrium. So this is our S process element. Then we have another alpha element in oxygen, and then we have another S process in barium. And this basically makes up most of the weight that XGBoost was giving to the elements. So this is telling us that if you measure iron, if you measure an alpha element like magnesium, and if you measure an S process element like yttrium, you're actually able to estimate the age of a star very well. And so those are the elements that you need when you're doing these chemical clocks. Now, the other thing that I should mention here is that the accuracy of the ages is improved by adding these other elements. So even though these don't have much weight, they do help beat errors down because the abundances, each individual element is not super precise in this measurement. All right, so I'll just leave you here with my summary. So the main take home is that chemical clocks work. Galah, with Galah, we can find abundances can be estimated directly just from age and metallicity to accuracies better than 0.03 dex, and we can turn that around and say, now we can get ages for the entire HR diagram to 1 to 2 gigayears, depending on your signal to noise of the spectrum. And so the fact that this even works at all has important implications on the history of the Milky Way. It says that azimuthal variation of metallicity must be kind of small. So stars born at the same radius all have roughly the same abundances, regardless of what azimuth or if they're along the spiral arm or not. And you can now get ages for a lot of stars observed by surveys. So if you're interested in dissecting the kinematics of the galaxy, this is a huge step forward for future studies.
Awesome, thanks, Michael. We have a question from Ella, and she's asking, do these trends for turn-off stars extend well to other types of stars? Could you elaborate a bit more on that?
Yeah, so the trends for turn-off stars mostly follow the other stars. So one thing I don't show here is that I also compared these ages to ages derived from astroseismology for giant stars. And we find pretty good agreement there as well. So the scatter is a little bit bigger for 2 reasons. One, astroseismology ages are not very precise. They're accurate to about 30 to 50%. And 2, Galah does have some systematic abundance trends in giants, for instance. So for giant stars, we still estimate ages. They're just not quite as good. They might be accurate to maybe 2 gigayears instead of 1 gigayear. And for dwarfs, the agreement does seem to be pretty good based on a couple of clusters that we have, that the dwarfs are performing the same as the turn-off stars.
All right, thanks. And Jake Clark is wondering, why would cobalt and zirconium and some other elements be terrible for chemical tagging?
So can you say, what did he say, terrible or?
Well, why would they possibly not work, especially cobalt and zirconium? I assume for Galah DF3 maybe, the data set that you used?
Yeah, so the elements I used were basically the ones that were most well measured. And so some elements do have information that I didn't use. But the main issue was I wanted them to be well measured across the HR diagram, right? So for some elements, for instance, like europium is a very, very good age indicator, but we only really measure it well for giants in Galah and not in turn-off stars or not in dwarfs. And so I wanted to use elements that were measured for all the stars because I wanted the ages to be roughly on the same scale in essence.
All right. Last question from Sara Martel. Does the Milky Way have the age gradients you would expect for a normal spiral galaxy?
Well, that's a very good question. I would say that is, and it's also very difficult to answer. Unfortunately, I do have maps of these ages in terms of R and Z, but I don't have a plot in my talk that shows it. But yeah, so basically you see that stars that are above the plane, for instance, are quite old. So your thick disk, your alpha enhanced stars using this method are going to come out old. So stars high above the plane are going to be old. Stars in the plane are going to be young. Stars in the outskirts of the galaxy are going to be younger than stars in the inner parts. So globally, that's true. But I think each galaxy kind of has probably a unique age distribution based on its evolutionary history when you really get into specifics.
All right, awesome, thanks. Good, thanks Michael again, and we're gonna move to Doug.
Hello.
All right,
Hello.
hey,
Hi,
great. Good, how are you?
Very good.
Right, do you want to start sharing?
I do.
Great, and then we can shift gears and actually move back to the sun or sun-like stars. And Doug has some insight in especially solar wind. So take it away, Doug.
Oops. I'm already messing it up. I just got this zoom bar like right on top of everything. I'm going to try and drag and drop it out of the way. That's better. All right. Hello, everyone. So my name is Doug Evensberget. I'm a PhD student at the University of Southern Queensland. And my talk is called Winds of Young Suns, and can we infer the history of the solar wind from stellar magnetic field observations? Let's try. Right. So at USQ, I'm part of the Starwinds project, which aims to produce the largest set of three-dimensional wind maps of young sun-like stars. And I think we can say that we've done this now. At the moment, I'm the only PhD student, but I have lots of help from postdocs and my supervisors and associate faculty and collaborators. So basically summarizing today's talk. So the strength of the solar wind in the past is not well characterized, but we can constrain it by studying young sun-like stars and trying to infer what their winds are like. What we do in this project is that we map the stellar surface magnetic field using Zeeman Doppler imaging. And we use the surface magnetic field to drive three-dimensional numerical simulations, which is, in a sense, the bulk of the work that I have been doing. Once we have the simulation results, we can create all kinds of maps. So we produce maps that cover the stellar corona and the inner astrosphere. And from the maps, we can calculate the stellar angular momentum loss, which determines the rate of stellar spin down. So this is largely determined. So the spin down is largely determined by the rotation itself, but it's also modulated by magnetic variations and magnetic cycles. So here's a plot of rotation versus age for sun-like stars. So after a stage of contraction where the stars actually rotate more and more rapidly, we enter into the phase from about 30 or so million years, where the dominant phenomenon is wind breaking, slowing down the rotation of the stars. For younger stars, they can form with different amounts of rotation. So they can be rapid rotators, up here showed as the blue curve, which can rotate up to 100 times faster than the sun, even more for some of these data points. But you can also have a slower, it can form with less angular momentum, which means it'll have a different trajectory. After about 1 billion years, all the stars are essentially indistinguishable from each other. They all follow this so-called schematic relationship, where the angular velocity is inversely proportional to the square root of the age. So this is caused by a feedback mechanism. Sorry. A feedback mechanism where the rotation rate is the main factor that determines the magnetic field through the stellar dynamo. The magnetic field and the rotation rate then determine the mass and the angular momentum loss of the star. Of course, the angular momentum loss is the same as the spin down, right? So this slows the star down. And that's what I'm calling the feedback mechanism here. And just this round and round causal relationship here. And as I said, the fast and the slow rotators forming with different amounts of angular velocity, they sort of converge by the age of about 1 billion years. There's also a relationship between the magnetic field strength and the rate of rotation, shown here for Zeeman Doppler imaging. So the same kind of measurements that I'm using, just the average magnetic field strength as a function of the period of rotation. And notice here that there is a spread here of about an order of magnitude in the magnetic field strength. So now that's just over here, the magnetic field is also affected by these modulations in the magnetic variation. Here I've plotted in gray essentially the same distribution of stellar rotation speeds as before. On top of that, I plotted the 30 stars in my stellar sample that I have created wind models for. So these are cluster stars, so they have known ages. And you can see that we have a few young ones and then a large number, a bit over 100 million years of age, and then some older stars as well. And the rotation rates, of course, this is expected, match well to the background gray distribution here. Here are the surface radial magnetic fields found from Zeeman Doppler imaging. From the left to the right, we have progressively younger stars, and also from the top to the bottom when they don't fill up an entire column here. So what we can see here is that in general, stars that have stronger magnetic fields, so sort of darker contrast here, they also appear to have more details in their surface magnetic fields, and particularly if they are also rapidly rotating. So this is a feature of Zeeman Doppler imaging, is that the more rapid the star rotates, the more detail you can resolve on the stellar surface. So in a sense, we don't really know if these are also more detailed and we just can't see it, or if older stars sort of have a less complicated magnetic field. However, we can try and shine some light on that through our modeling. So that's the input that I use to drive all my wind models. Here's an example of an image from after I have run the MHD simulation. So the background here is the wind speed, just in meters per second. We also see two features that are kind of classic to draw in this field. The Alfven surface is this sort of two-lobed shape here. This is essentially when the angular momentum loss, if you think of the angular momentum loss as sort of occurring with the lever arm from the star itself corresponding to the distance to the Alfven surface. That's a pretty good approximation. So a larger Alfven surface means a larger angular momentum loss. This gray translucent surface that you can also see here, this is the current sheet. So that's essentially, in my models, this is simply where the radial magnetic field strength is 0. So here's the 30 stars after the models have been run. So again, we can see some trends here. So in the top left, we have, or in general, we have these two-lobed Alfven surfaces. We do see that as magnetic fields, there's a trend for stronger magnetic fields towards the right and towards the bottom. This is also reflected in the larger Alfven surfaces and consequently the larger torques. We see that the inclination of the Alfven surface is actually varies a bit all over the place. Some are 90 degrees inclined to the rate of rotations, and other are pretty much aligned with the axis of rotation. Sorry, I said rate, axis of rotation is what I meant. If you have a rapid rotator that is also has a large inclination, then you'll get this wrapping of the current sheet around the star, such as seen here. There's two sort of oddball stars here, BDO7 and LO PEG, and they are special in that they have very rapid rotation. We'll see that later as well. So, so some of these sort of, if you can't see it so well here from the side, but they're sort of the Alfven surface is pulled into a bit of a spiral shape as well. So now, looking at now we can look at the torque, so or the angular momentum loss, so the spin down of the star, just as a function of the average magnetic field strength on the surface. So that's what I'm plotting here. You see this one has a very high angular momentum loss, while the sort of more tepid ones, they tend to lie towards the bottom here. It's very notable here that there's a large residual here, 8, so it's 64. It's sort of a factor of 8 on either side here. So, so plotting like this, there's a large amount of angular momentum loss variation that is not explained by this average magnetic field strength. We can sort of do a bit better than that. I have to speed up a little bit. So if we just divide through by the current rate of rotation, we get a much closer fit here. And also considering the flux, so basically the field strength multiplied by the surface area of the star, we get a residual or variation of about a factor of 4, so +2, -2. It's 2 minutes, right? So I still have 2 minutes, that's good. The main sort of thing that we would be interested perhaps on the young Earth is this quantity called the magnetospheric standoff distance, which is the distance from the planet to where the Earth's magnetosphere sort of meets with the magnetosphere of the star. So it's often said that this value has to be sort of under 4 before there is a real risk of atmospheric erosion and these kind of phenomenon. So we don't really see, even for the most rapidly rotating and magnetically active youngest stars, we don't really see that there is a strong risk of that, at least for the steady state winds that I am modeling here. Finally, we can sort of take now the angular momentum loss values that we calculated from our models, and we can compare it to the tracks that we should have from the stellar rotation from the Galton Bouvier that I showed initially. And these little line segments, they kind of show in what direction these stars should be moving on this plot, given that all my modeling is correct, essentially. And you see here, for example, this N here and L, they point, they're sort of moving in different directions here. And this variation, we believe, or I believe, is caused by the magnetic geometry. So not so much by the field strength, but difference in the field complexity. And the thing that you have to consider then is that these variations have to be transient. So we can't have this star sort of breaking too little for too long, right? It'll sort of be going out here, then like M, the one I'm showing here. So all these kind of variations, they essentially have to be short term, and the average essentially should point along these gray background curves here, because otherwise we wouldn't see the convergence at 1 billion years of age. We do also see that the stellar observation may underestimate the field strength for slower rotators. This is something that other people have observed with Zeeman Doppler imaging as well. And it's interesting to see that on this particular plot, how some of the stars in the coma and the Hyades, these about 600 million years, they don't have sufficient angular momentum loss, although there's also one here that has a very high value. So here there is room for some more experimentation and modeling, I think. But otherwise, it's satisfying to see that the angular momentum loss values that we've calculated essentially sort of kind of match up with the rotation curves. So I don't know how I'm doing for time, but it's probably not much left. Thanks, everyone. And yeah, if you are interested in this, then have a look at our paper, which is accepted. It's a sort of, it's not yet, it's only available as a PDF, and it's been like that for a while, but hopefully one day it'll also be HTML. Thank you.
Awesome. All right. Thanks, Doug. We actually have already 2 questions coming in. Great. Christine is asking, did you calculate mass loss rates? And if so, how do they compare to the results from Wood et al. Using Lyman alpha or the upper limits from the radio? So for example, Fichtinger et al.
Right.
If you know these
Yes.
studies.
So Wood et al. is a sort of famous study, and basically he extrapolated backwards from the mass loss of the sun today, and he found that as he moves backwards in time, there's a sort of match between observations and the model, but at a certain age, this thing called the wind dividing line, and after that, he observes much smaller mass losses than what is predicted from his initial sort of fit. We do see that the mass loss is sort of peaking. We see a sort of saturation in mass loss, that the curve doesn't just go straight upwards, but it curves at about 20 solar masses or so. But I think what we have to think about there is that so my models are essentially steady state models. So there may be transient phenomena on stars that cause a much larger loss of mass and also angular momentum, by the way, than the steady state. And yeah, this is also definitely an area of further research, because simulating steady state or looking or real time dependent models is much more complicated, or takes more time.
Yeah, I'm going to ask one more question from Thomas Norlander. He's saying, it looks like the rotation of solar type stars is basically erased by an age of about 1 gigayear. Does this mean we have no way of figuring out which of these rotation curves that you show here the sun actually evolved along?
Yeah, so that's why there's a question mark at the title of the talk, because the only thing that we can say, essentially that's correct. What you're saying is correct. The only thing that we can say is that if we sort of naively model angular momentum loss of different stars of the same age, and we find this big spread, so shown here by the difference in the direction of these little line segments, this is probably transient, because if they lasted for a long time, then we wouldn't see this nice curve. So that's something that we can sort of say that, oh yeah, magnetic variations should be short-lived magnetic cycles compared to the lifetime of the star rather than permanent differences. But other than that, I would be very interested if you have some way of figuring out what the sun was, if it was a fast or a slow rotator. I don't think that's known.
All right, great. We have 2 more questions from Jake and Daniel that you will sadly have to answer in the Slack because we have to move on and go over to Mike. Hi, Mike, I can see you. Great, awesome.
Hello.
And we can hear you, great.
And I'll just begin, I guess.
And now we can see it as well. All right, thanks, Steph. And yeah. Feel free to go ahead, Mike.
All right, thank you. So hello, everyone. Well done for making it that far through the day. I'm Mike. I'm a PhD student at Monash University. I'm also part of OSGRAV. And it is my pleasure to be giving perhaps one of the last live talks of Melbourne. And I'll be talking about 3D hydrodynamical simulations of a massive star common envelope. Now, this is work done in collaboration with Ilya Mandel, Rio Hirai, Daniel Price, Orso DeMarco, and Miguel Gonzalez Bolivar. So first of all, there's a lot of things to unpack here. Actually, let me try to move the Zoom video window because that seems to be blocking the slides. Thank you. Seems to be better now, so I'll continue. So what a common envelope is basically you can have a star inside a star. So yesterday, I think we've heard about that. We have a galaxy inside a galaxy, but now we have a star inside a star. Now you might ask, how do you get the star inside a star? Isn't that just a merger? If you put a star close to another one, it will just merge and become one bigger star. Well, it turns out you can actually avoid this situation if one of your stars is really big and fluffy. So you can actually put a smaller star inside the envelope of this star and have it swim through the envelope like swimming through honey. And this is what a common envelope phase is. So a common envelope evolution occurs in a binary star, so that's two stars in orbit with each other, and it occurs when a companion star, one of the stars, enters the extended envelope of a giant star. Now I'll call the giant star the donor. And inside the envelope, it will orbit the core of the donor, of the giant inside. And during this process, the companion will experience drag forces in the envelope, and these drag forces will dissipate orbital energy and angular momentum. And if enough energy and angular momentum is dissipated, this process may expel the envelope and leave behind a much tighter binary system that now consists only of the core of the donor and the companion, shown in the bottom part of the figure. Now, why should we care about common envelopes? Well, common envelope evolution is actually thought to be the dominant formation scenario for tight binary systems that involve compact objects. And that includes gravitational wave sources, binary black holes and double neutron stars that will merge in the lifetime of the universe. And also actually a lot of other fun things, including X-ray binaries, progenitors of type 1a supernovae, and more. Common envelope is actually one of the most important phases in binary evolution, in that it's very transformative, but it's also one of the most poorly constrained processes in binary evolution. So over the past several decades, there have been numerous attempts to model common envelope. Some of these attempts are in the form of detailed hydro simulations. Some of these examples are shown here on the slides. And these simulations primarily seek to address some few key questions. The first one is that whether we can actually simulate the ejection of this common envelope with hydrodynamics. And if we do eject the envelope, what is the final separation of the system that's left behind? That's an important question because it determines, for example, in the case of gravitational wave sources, whether we would make a binary that could merge in the lifetime of the universe and give us lovely gravitational waves. However, these 3D simulations are notoriously difficult for several reasons. First of all, there's a very large dynamical range involved. You have to simultaneously resolve the very dense stellar core of the donor and also the initially wide orbit of the companion around the donor star. And where performed, these simulations have largely been unsuccessful in unbinding the entire envelope self-consistently. Moreover, these simulations, such as the ones shown on the slide, have mainly focused on low mass donors of about 1 to 2 solar masses. But if we ought to understand the formation of X-ray binaries or gravitational wave sources, which came from massive stars, we really ought to understand common envelopes that involve a massive star. But you might ask me, Mike, what's the big deal about just running a simulation with a larger star? The answer is that we expect massive star common envelopes to be qualitatively different. It's not just a heavier star, because, for example, there is radiation support in the envelope of massive stars. As an example, we can look at a 12 solar mass red supergiant here and ask how bound is the envelope, how easy it is to eject this envelope in a common envelope interaction. And the binding energy, we can do that by looking at what the binding energy of this envelope is. And that depends on both the gravitational potential energy of the envelope and also any other possible internal energy in the envelope. So the anticipation is that part of this internal energy could be converted into the kinetic energy of this envelope that helps it be ejected from the system. So what are the sources of internal energy? Well, first of all, there's gas pressure and gas internal energy. But we're saying that in massive stars, there would also be a contribution due to radiation. So radiation contributes some thermal energy. And For a 12 solar mass red supergiant, you can actually lower the binding energy by 24%. So the envelope is 24% less bound. In fact, there are also other sources such as recombination. So if you add in the effects of recombination, and I've represented this by a series of time bombs inside the star, because what happens is that this energy is stored inside the envelope, and when you cool below the binding energy of the electrons, they combine with their ions, and that releases energy that could possibly be used to eject the envelope. And if you add in this into your calculations, your binding energy could be another factor of 2.5 lower. So the takeaway is that firm internal energy could be used possibly to eject the envelope, and in massive stars, we have the additional contribution of radiation. So how do I seek to quantify the effects of radiation pressure and of recombination in a common envelope? The method we're taking is that we're performing a series of simulations, but with different equations of state. So with 3 different equations of state here, the first one being just an ideal gas equation of state, the second one being gas plus radiation. So we add in the contribution of radiation. And the third one, a full equation of state that adds in both gas and the effects of ionization and recombination. So the idea is that if we compare 1 and 2, that would reveal the difference between a low mass and a massive star common envelope, namely the effects of radiation. And if we compare 2 and 3, that would reveal the role of recombination itself. So I've performed these detailed simulations with the code Phantom, which is a smooth particle hydrodynamics code. And Daniel Price yesterday has shown us some beautiful simulations of tidal disruption events made with Phantom as well. And on the right of the slide, I show here the setup of our simulation. The big yellow sphere is our 12 solar mass red supergiant donor. And it is in an orbit with a companion that's represented by a point mass. So I'll now show you some movies of my simulations. So again, you can see the donor star here, the red supergiant. And the companion is not quite visible yet, but as gas is transferred to it, you would see it will become more visible. So I'll play the movie now. So this is the phase of Rochelot overflow. Gas is transferred to the companion. And it settles around in a small disk around the companion. So after many orbits or so, I pause at this point where the companion is first about to enter the envelope of the star. So this is really the start of the common envelope. And I'll show this from different perspectives. This is the start of the so-called plunge in. And the subsequent evolution occurs very quickly because you start feeling this drag force, which causes the orbit to spiral in very quickly. So I'll play the rest of the simulation here. And you get a big puff of the common envelope being ejected. This is a similar movie, but showing a density cross-section, looking at the orbit face on. And in this movie, it nicely shows the spiral wakes formed by the companion in the orbit. And so these are some qualitative results. So I'll now show some quantitative results, which is, again, this is just a separation time curve. So it plots the distance, the separation between the core of the donor and the companion as a function of time. So the initial flat bit corresponds to where the companion is still outside the envelope. And there's a rapid drop-off that occurs after the plunge in when the companion enters the envelope and feels a lot of drag force. And the final separation is given by this end bit here, which determines the final state of the common envelope.
You have 2 minutes, Mike.
Right, thank you. So we can also look at the same plot, but comparing our runs with different equations of state. What we find is that as we go from the red to the green line in the diagram, we're going in the direction where we add in radiation and recombination. And so that's in the direction of decreasing binding energy. And we find indeed that we have a trend where the final separation increases. So it's easier to eject the envelope when we have when the envelope is less bound because of the additional internal energy. We see a similar trend in the unbound mass. So here I plot the fraction of unbound envelope mass as a function of time for the 3 different equations of state. Again, we're decreasing our binding energy from left to right because we're increasing, we're adding in the effects of radiation and then recombination. And we also find, so we find here that not only do we increase the final separation, we also increase the amount of unbinding of the envelope. And in the case of the full equation of state, where it includes recombination, it even seems that we're able to completely unbind the envelope, at least for our lowest resolution case. So I'll give a summary of my talk here now. We've produced one of the first 3D global hydro simulations of a common envelope interaction that has a red supergiant. And we've compared the results obtained assuming 3 different equations of state that include various different forms of internal energy. And can we fully eject the envelope? The answer is perhaps, and that we see that radiation and recombination energy definitely helps. And what is the final separation? The answer is that the result of a study is that it depends on the equation of state. We're able to stall earlier in the common envelope if we include more internal energy. And that's it. And I'll leave you with this animation of post-common envelope nebula that we get from our simulations. All right, thanks, and I'll now take any questions.
Thanks, Mike. Awesome, really awesome. Thomas also agrees, fantastic talk. I assume it's not possible to run the full simulation with bells and whistles over a long time, but is it possible to cheat and see what this looks like after thousands of years?
Yes, there are many ways to cheat, I guess. And we're still thinking of new ways to cheat. One approach that people have thought about is just to map everything back into a 1D stellar evolution code, for example, because you could add in more physics and you can run things for longer, like thousands of years in these 1D codes. And it's less obvious how to do that in 3D. So at the end of our simulations, there is some really dense gas that's near the core of the donor, and that slows down our simulations a lot. So yeah, the answer is that we're working on that, I guess.
All right, great. All right, Adela has a question. Can you calibrate the alpha parameter using your simulations? And can you also explain what the alpha parameter is for me, at least, if you understand the question?
Sure, yeah. Might have a bonus slide on this. So this is exactly what the alpha parameter is. So in that equation, this is sort of a back of the envelope way of determining what is the final separation in the common envelope. So in the form of a global energy conservation sort of way, the change in orbital energy between the initial and final states of the common envelope must equate the binding energy of the envelope, because that's what you're getting rid of. And so, but however, if the orbital energy is not used completely efficiently, we don't expect this equality to be true. And so we add in a fudge factor, which is called the alpha, or common envelope efficiency. So to determine alpha, all we need is to determine the final separation and measure the binding energy of our envelope, both of which we could obtain from our simulations or from our stellar profile. So in our simulations, we do get alphas of order 1. And if we just include the potential energy in our binding energy of the envelope, we see that alpha increases with as we go from the ideal gas to the full equation of state. And that's one of the qualitative results that we're seeking in this study, that there's some of the internal energy could be used to eject the envelope. And if we include the thermal energy in the binding energy of the envelope as well, we get alphas of order 0.6. So that's just saying that the thermal energy isn't all used to eject the envelope. There's some inefficiency in there, which is not completely unexpected.
Right, thanks. Also, thanks for the prepared slide. I would say the last talk of the session goes to George, who asks, do you have any idea what fraction of common envelopes eject the envelope from your simulations?
Is that some, sorry, could you repeat the question again?
Yeah, what fraction of common envelopes eject the envelope from your simulations?
from my simulations. So that depends on the initial setup of the common envelope. So again, you can sort of predict whether you could eject the envelope using this alpha formalism, using this equation I've shown here. And we've actually performed two sets of simulation, one with a larger mass for the companion, one with a smaller companion. In the case of the smaller companion, we actually don't eject the envelope. So what happens is that